All right, this section is about finding derivatives of common functions like sine, cosine, e to the x, and natural log of x. These are not derivatives we'll prove today, but these are derivatives that you are responsible for knowing. Okay, so first, we're going to practice kind of our skills of sketching graphs from sketching derivative graphs based on the graph that we have. And so here is a graph of a familiar function. I hope you recognize that graph as the graph of e to the x. And if I want to make a graph of the derivative, then that means that at each of these x coordinates, I'm going to estimate the slope. So at x equals -5, it looks like the slope is almost 0. At x equals -4, it's also almost 0, maybe a little bit bigger, but not much. And at x equals -3, there's a little tiny bit of slope. At x equals -2, it looks like it's, like a little bit up, maybe not quite a fourth. And at x equals -1, it looks like the slope, like if I count rise over run here, it's a little bit under a half. So I'm going to make that point just a little bit less than a half. And at x equals 1, it looks like, at x equals 0, it looks like the slope is about exactly 1. At x equals 1, it looks like the slope is maybe a little bit more than 2. So if I sketch a graph of the derivative, you should be noticing, what? It's the same as the graph of the function. So that is our first derivative. The derivative of e to the x is also e to the x. So it's my calculus book when I was in high school said it's turtles all the way down. You keep taking derivatives, you're going to keep getting e to the x. So the derivative of e to the x is just plain old e to the x. Here's the next one. I hope you recognize this function as a trig function, and it is the sine function because it starts at 0. So here's a graph of sine of x. And now if I imagine tangent lines, at 0 it looks like it has a slope of 1. At, I'm going to call this, pi over 2, it looks like it has a slope of 0. And again, at about pi, it looks like it has a slope of -1. And then here again at 3 pi over 2, it has a slope of 0 again. So here's kind of our shape. And it continues in the other direction as well, with our next flat spot being at negative pi over 2-ish. So I hope you recognize that as the cosine graph. So it turns out that as long as you're in radians, the derivative of sine is cosine. I'm not going to go through the cosine one, but it turns out that derivative is negative sine. So you now have 3 new derivatives that you're allowed to use: the derivative of e to the x, the derivative of sine, and the derivative of cosine. Finally, and this is a graph that you may be a little bit less comfortable with, but this is a graph of natural log of x. And I'm noticing that at x equals 1, we have a slope of 1. I'm also noticing that all of these slopes are uphill, and that at -5, at x equals 0, our slope is approaching positive infinity. So we're going our slopes are getting really, really steep and then shallowing out until they get to x equals 1. And then the slopes are approaching 0 the further along we go. So it looks like this if I make a rough sketch of the derivative, which may or may not be something that you recognize, but it's part of a hyperbola. So I'm sorry, I guess I called that g. So g prime of x is 1 over x, but only for x is greater than 0. It's not true. It's not the other part of that 1 over x graph. But the domain of natural log is also x is greater than 0, so that's why we don't have to worry about always saying that. So if your function is natural log of x, then the derivative of your function is 1 over x. Notice that x is always going to be greater than 0 in this case, because otherwise you'd be outside of the domain of f, and there's no derivative if you're outside of the domain. Okay, I have a couple of examples to end with today. So what is the equation for the tangent line to f of x equals cosine x at x equals pi over 3? So tangent line, I need three things. I need an x coordinate, got it. I need a y coordinate, which would be cosine of pi over 3, which would be 1/2. And then I also need a slope, and the slope is the part that's going to take calculus. So the slope would be f prime. Well, look it up if you don't have it in front of you, but the derivative of cosine is negative sine. Oops, I didn't write pi over 3 here, but that's what I was doing. And sine of pi over 3 is 1/2, so negative sine of pi over 3 is, no, it's not 1/2, it's root 3 over 2. And so now we have the three pieces we need to write an equation for the tangent line. So y equals negative root 3 over 2, x minus pi over 3, plus 1/2. And no reason to go any farther than that unless it's multiple choice and you have to find your match. But we'll stop there. And then the second example is asking you to evaluate this limit, but it's not really asking you to evaluate the limit, because this looks a lot like the limit as h goes to 0 of f of x plus h minus f of x all over h, and we know that that is f prime of x. But in our case, x would be 2, and f of x would be natural log of 2. Sorry, not natural log of 2, natural log of x. So this crazy limit here, which I don't know how to evaluate on its own, is really f prime if f is natural log of x. So it's going to be 1 over x, 1 over x, and x is 2, so f prime of 2 would be 1/2. So this crazy limit goes to 1/2, and I only know that because I happen to know that that crazy limit is the derivative of natural log at 2. The College Board actually does this a lot, and rather than they don't really ask you to find a lot of limits. Sometimes they do, but not a lot. And often what they're really asking you to do is recognize that it's not really asking you for a limit, it's really asking you for a derivative. Test yourself by trying to match the function, which are graphed here in orange on the left, with the derivative, and see if you can do that. I will recommend that you pause the video and then I will reveal the matches. So this is pretty messy, but these are the matches. And you know, that skill of being able to read a graph and say, well, I noticed that this graph of cosine has a 0. The derivative would have a 0 at each of these places. And now if I look at negative sine, it has zeros at each of those places that I marked that were zeros for the cosine. And this graph of cosine starts out downhill. So our graph's downhill means that the derivative is below the x-axis and then uphill. So it's partly just knowing the functions, but it's also recognizing those uphill, downhill, and recognizing how to get from a graph to the derivative. I didn't actually prove any of these. And part of that is that the limits for proving them are complicated and maybe not worth the time. But if you're interested, they are certainly Googleable and you can prove them. But in order to prove all of them, you have to go back to the definition of a derivative and do that limit. And prove to yourself that that limit goes to the function. All right. Good luck.